Hello, that would be me. Thank you very much for coming. And we are going to talk about from iterators to ranges. So that's going to be how the C++ library is going to evolve in the coming years, moving maybe away from iterators or augmenting iterators by ranges. Now, first of all, who knows ranges? Hands up. Boost range. Eric Niebler's range. And who already uses it every day, where it's basically a normal thing to do in everyday programming. Not that many. That should change. Ranges are fantastic. We use it in our whole code base, and it makes for really nice code. Now, first of all, why do you want to have ranges? Well, in regular C++, you would write something like this. You have a std vector and you fill it somehow. And if you then want to remove all the duplicate elements, the usual motions that you go through is you first sort this thing. And there you have to say vec begin and vec end. And then you remove all the duplicate elements by std unique, which actually compacts all the elements that are duplicates at the end of your range. And then you have to throw these away. And if I'm counting correctly, it's like 1, 2, 3, 4, 5 times I actually mentioned vector begin or vector end, which is really not what you want to do. This is verbose code. Now, first of all, or additionally, there's a bug in this code, in the 3 lines up there. What is it? How do you sort? What do you need for sorting? A predicate. Which predicate? Less. Now, std unique is using which predicate? Equal. So there's a mismatch here between the predicate we're using for sorting and the predicate we're using for unique. And that is a potential problem. You don't want to have that. You want to be consistent. Maybe you want to say, okay, my programmers should do this consistently anyway. Well, that's great, but there's just no reason to be inconsistent here when you do such an operation. So when you replace that with our range equivalent, tc unique in place, tc sort, of course, the tc unique in place, it's actually not unique in place. You would call it maybe ordered unique in place, and that would actually assume, okay, we need to do something here with the predicate. We have to use the same predicate in both cases, because unless this thing is sorted with the predicate, of course, the unique is not going to work. And you're only going to mention vec once. That's cool. So why do we think we know something about ranges? Well, we started off with boost range when we started a product, because we kind of liked the way it worked. And by now, we have about 1 million lines of code of production code. And we use ranges in this 1 million lines of code everywhere. Now, the nice thing is that while we are building our production code, we can change the library. And we can change the library while we're working our production code. They evolve together. So anything we learned in that 1 million lines of production code flowed into the library. And we were free. We have one guy who is doing nothing else but refactoring code. So if we have to change the library, we simply do it. We have that freedom. So I think during that process, we learned quite a bit what it does mean to have a good range library. And that's basically what I want to show in this talk. First of all, what do we have in terms of ranges right now? It turns out not terribly much. C++11 gave us the range-based for loop. And it gave us universal access to begin and end, so it also works in arrays, except that, well, even that std begin and std end doesn't really work because they kind of forgot ADL. So you have to always write using std begin and then begin in order to get the thing that you probably expect. And that's it. That's what we have currently in the standard. Now, there is a ranges TS, a technical specification in the standard, or from the standard committee, which is a part of what Eric Niebler is doing. Eric Niebler is currently driving the ranges in the standard, and I will point out the things that we think should be done differently. Still, he drove the ranges TS, and it basically is a range extension of the standard library. So you have all your algorithms that usually take pairs of iterators, now can take ranges. So you can write something like a find with a range as a first parameter. And then there is the range v3 that he currently has published on GitHub, and there is actually just now in February there is a paper that he submitted to the standard committee, which has some more parts of what he wants to standardize, but we'll talk about this later. Now, first of all, what are ranges? Ranges, first of all, are everything you know as containers. So a vector, a string, a list. They have their usual container semantics. So if you copy them, you copy the elements. So copying is O of n. They own the elements. So if you destroy them, the elements go away. And you have deep constness. If you have a container that's const, then you can only access the elements const. Now what else should there be? There are views. And ranges are then really containers together with views. So that's what's a view? Well, a view is anything that you have seen so far in terms of iterator pairs. Any of the things where you pass in iterator pairs are views. They reference the elements. They don't own the elements. They only point at them. And what you're really doing with a view is you combine this iterator pair into one object. Not too exciting. And they reference the elements. You get shallow copying, just like if you would copy the iterators, and you get shallow constness. And really, this iterator range up here, that's a simple view onto anything that you would have iterators to. Okay, well, views would be pretty boring if that would be it. But you can do more interesting stuff with views. You have, for example, range adapters. So here's the problem before I describe the solution. Say you have a find on ranges, and you plug in your range, and you plug in what you want to find, and it spits out an iterator of where it found it. So far, so good. Now, let's say you want to do this. First, you do this on an int, and you're looking for the 4. That's fine. You can write this quite idiomatically, like up there. Let's say you want to do this on a struct, and you want to project on a struct, on one of the elements of the struct first. The way you would write it right now is you would use a different algorithm. You would use findIf instead of find, and then inside your predicate, you kind of do two things at the same time. You are accessing the id out of the A, and you're doing the comparison. So there's really a munging together of two things which are rather separate. And one of the things, the comparing to the 4, we already did up here, but with a different syntax. That's kind of ugly. You would like to have that syntax here to be reusable for this kind of use case. And enter the transform adapter. So what the transform adapter does is you give it a range, and while you're iterating over that range, it would apply a function to the range and return its value while you are basically iterating. And this way, you have separated the way of projection, your function of projection, into that TC transform here. You transformed your vector with that functor, and the result of that, you are finding the 4 in. And one important thing is that the transform operates lazily, right? So you start iterating, and only while you are actually dereferencing your iterator, it will actually invoke the function and get the result out. So there's no allocation happening here or stuff being copied. It's basically all happening on the fly while you're running your find algorithm. Okay, there's one little caveat which I want to point out here. Now, when you have that iterator coming out of your range's find, what is it pointing to? Well, it is pointing to int, right? Because the range's find was operating on a range of ints, which is the transform. What you want to do is you want to unwrap that iterator and free it from its transform. So you need some sort of base functionality. You need to be able to go from the iterator to the transform to the iterator of the base range. So usually the iterators have some sort of base functionality. That was the name that they used in boost range, and we kept it. So that's something you certainly need. Now, how is that thing implemented? Here it becomes a bit more interesting. So the naive way to implement this, and this is how it was done within boost range, is the transform range has an iterator. And since the iterator, while it's dereferencing, has invoked the function, kind of the naive implementation is to just carry around the function in every iterator. So every iterator not only carries around the base range, right, or the base iterator here, that's where it's taking its value from, but always also the functor. And when you're invoking the dereferencing, the iterator would be dereferenced and plug the value into the functor. Functor operates on the value and returns whatever it returns, and that's what's being used in the range. Okay, let's look at another interesting adapter, and that's the filter adapter. And these two, the transform and the filter, are really the bulk of what we use for ranges. That already covers, I would say, maybe 80% of the use cases. So let's say you want a range where the ID is 4. You want to filter the range and pick all the elements where ID is 4. So here you have a filter, you have your V, which is your vector of ints, or your vector of A's, in fact. And here you pick the A's where the ID of that A is 4. And you would write it this way. Again, it's lazy. While the filter is executing, you execute the filter, and every time the way it works is every time you're incrementing, you basically have to skip the values that you don't want and pick the value you want, and there your iterator would stop, and then you can dereference this and get your value. So far, so good. Now, this would be the implementation. Again, the iterator needs to carry around the functor, and it needs to carry around an iterator to the base range, where it currently is in its iteration. And, well, the problem is, when you're starting to iterate, you skip the current value, and then you keep going until you find something that matches your filter. Well, if everything all the way to the end doesn't match your filter, you have to be darn careful that you don't fall off the end. So what you need to do, well, you need to somehow keep the end iterator around in addition to the iterator where you're currently at. Okay, so our iterator now has the functor and 2 underlying iterators. How does the iterator look like of this thing? Well, like this. Now, you had a functor and it has iterator, and the iterator has a functor and an iterator, and an iterator, and in the end you have an end, and you have an end, and you get an combinatorial explosion, exponential explosion of the size of your iterator. If you have 10 of these, you get gigantic iterators that you're going to move through your for loops, and that's probably not something that you want to have. But that was the state of the art of boost range. They actually did that until someone noticed. Now, that's not so fantastic. How can you do it better? We wanted to do it better because we wanted to use that in real code. Now, you must keep your iterators small, okay? Now, they did something in the standard, and I think it was because we actually brought up this problem. They said, okay, the iterators are going to stay valid even for views, only as long as the view stays valid. So the iterator lifetime is tied to the view lifetime. What does that buy you? Well, that buys you that you can keep stuff that is common to all iterators in the view object. And that's great. So now we can put the functor and the iterator end, both of them, in the view object, in the adapter object. And the iterators, they only have an iterator and a pointer to their range. That's a bit better. Not bad. But still. We have this. So we have a filter and a filter and a filter. Well, every one of these iterators has their own base, right? They're all different because you got 3 filter objects, so you got 3 pointers to your view object, to your filter object. So you got still linear growth of iterators. If you stack 10 of them, you're still moving around maybe 20 words of things, which is not great. So something was missing here. There was something conceptually missing on how to stack adapters efficiently. And here's what we came up with. You need to get away from the iterator concept. The iterator concept itself, just having an iterator all by itself doing stuff, I don't think you can be any more efficient easily than what we previously saw. We said, okay, we're going to move from iterators to indices. We call them indices. They're different from iterators in that they need their base object to do something. So it's not like they are carrying around the base object. You need to give it to them. And then you can actually do the operation. So typically, you would have on your base object, on your range, you would have things like, okay, you give me the begin index, end index. But for example, for increment index, you would plug in the index into a member, say, of your index range. So you have both, you have your range and you have your index. And together, you can increment the index. Now, all good, but, well, it's not compatible with iterators, and you don't want to change your whole code. But bear with me how we're actually going to use that. Now, first of all, we're not going to change the world, and we're not going to make everyone use indices with a different interface, maybe less convenient, and no longer use iterators. It's just not feasible. It's not going to happen. But it's pretty easy to wrap any index and create an iterator out of them. Because all you really need to do is you need to carry around, again, the pointer to the base range. So you have an index, and then you have the pointer to the base range. And together, these two can then actually implement any iterator operation. For example, here, increment, you can just go to your base range and increment index of the index. Now, maybe this sounds awfully like what we had before, but it's different because you're only going to do this wrapping on the very topmost of your stack of actual indices that of filters and adapters that you actually stack together. So it's quite a bit different. Now, and how does it help you to actually do the filtering efficiently? So here we have the filter range based on indices this time, and you want to carry around the base pointer where the base or the range that you are filtering. You're only going to carry this around in the filter range, and your index is always effectively just going to be the index of your base range. So if you are filtering a vector, and you filter it and filter it again and filter it again and filter it again, filter it again, effectively your index is going to be no more than a pointer to the buffer of your vector. It's never going to change. You just pass the index all the way through. And incrementing then requires you to access the base, which you can ask to increment the index. And the information of what your base is and what the end of your base is going to be carried around in your base. It already knows. So you are essentially then stacking these view objects. The index is going to be really small, and you can still perform the operation that you need. So, and then you turn the index into an iterator. So all the iterators, regardless of the stacking depth, are going to turn out to be just 2 words. One is basically the index, which is the pointer to your say vector, your really container iterator, if you will. And then the other word is going to be the pointer to your adapter object. And there you get all the other information from. So that way we got these adapters to actually work efficiently. And the index is not part of the standard, but nothing precludes you to write something that is standard conformant using this kind of index concept. There is also a slight difference between us and what's proposed in range 3.3 regarding the treatment of rvalues. Now, let's say you write something like this. you say, okay, I'm going to filter the vector with a predicate, and this range is a lazy range. You can iterate over it, and while you're iterating, it will actually invoke the predicate and give you the result back. And then you can invoke some algorithm, say any off on that range, and get your result. So all of this here is lazy, and also the range is only referencing the vector. So the vector here has to stay alive for this to work. If the vector goes out of scope before you run your any off, you're out of luck. Let's say we don't have a vector here. We're just creating one. So the vector is an R value. The problem is, if I'm keeping inside my filter a reference to the vector that I just created, then I just created a dangling pointer, because my vector is going to go out of scope as soon as you exit the statement, and I'm going to have a dangling reference. Well, that's not good. So how do we deal with it? Now, range v3 says views are non-owning. They reference their values. So if we want to stay pure and stick to this concept, we cannot really allow that. We make this not compile, because it's an R value. You cannot have a pure view that references the container if the container is an R value. It's going to go out of scope. So we don't do this. We don't compile. Fix your code. Okay, I'm going to fix my code. Now, this actually compiles. This is an alternative that they actually have in their library. So there are views and there are actions. And actions can deal with R values, but they're eager. So if my programmer writes this and says, shh, doesn't compile, it's going to fix it. I fixed it. Now it compiles. Fantastic. Well, you just broke it, because your laziness is out the door. The any off is usually lazy, right? As soon as it finds something, it'll abort and say, yep, it's any off is good, true. It won't do that anymore, because it will now execute actually the predicate on all the values, and it will do the whole filtering and memory management and everything, right? Just to say, oh, my first one is already true. Thank you, I'm done. I didn't need all that stuff, but thanks, you produced it for me. Well, this is not what we want to do, okay? And that's something that bit us quite early in the development, that we needed a solution for that. So we reduced our purity level. We said these adapters can actually be containers. So what we do is, if the adapter input that we have into our filter is an L value, the regular case, then the filter is going to create a view. It's just going to just reference the input. And then we have one copy and shallow constant and all this kind of stuff. Now, if the adapter input is an R value, then the TC filter is going to take that container and aggregate it, copy it into itself, and carry it around as if it is a container itself. So it's going to have all the properties of a container. It'll copy and then copies the elements. But it is always lazy. And that's important here, because basically what I think is important is that laziness and containerness are orthogonal concepts. We should actually keep these separate. And Eric Niebler's library doesn't do that. He's basically insisting, okay, whenever I have a lazy view, then that's always a view. It's a lazy view, or it's eager and then it's a container. But I think that's too strict. I think what he was worried about is that people kind of would expect that filter produces a view. So what happens when I'm taking this view that I just created, or this thing that I just created, from an R value, which is now a container, and I expect it to be a view and I start copying it. Okay, point well taken. We found that this is not really a practical problem. So we actually have the same syntax. It's just going to be TC filter, and you either get a container out or you get a view out. And the case of actually accidentally generating copies of stuff that you really wanted to reference didn't really be a problem is not really a problem in our code base, and it's quite large. So that was that. I want to talk about something else that we basically did beyond the range v3. The algorithms can often be a bit more flexible in what they return. So we already take only a single object that we plug into the algorithm. We take the range instead of the two iterators. And it would be kind of nice if we could carry this through to the result of an algorithm. Say if you have a find, okay, and usually what you would do is you find the iterator where that your condition is where you found the what that you passed, and you return that iterator, otherwise you return end. So you end up with a single iterator. Well, that's not always practical. Sometimes what you would like is, so first of all, you can make this more you can basically separate the way that how you generate the iterator, the finding part, from the returning part. What do I want to get out? Right now, you always get an iterator out. But, I mean, we've written things like, okay, we do a find, and then assert blah, blah, blah is not end, right? Because we know that this should be actually in the container. So you either get the iterator or you get end, but then, oh, no, I don't want the end. Well, why do I have to write this every time? Can't I just specify, and that's what you're doing here with a struct, what I want to get out. I say, okay, either you want to do iterator or end, or if I only want the iterator and I don't want the end, I can just plug this into a pack template into my find, and I just then I'm basically get the assert already in the actual function call. So I would write find brackets and then return iterator, and that way I say, you know, don't give me an end. If you give me an end, that's undefined behavior. Give me an iterator. You must find this. I want to assert away the other case, and that's how we do it. So you have the struct. You say, okay, return iterator. The pack says, how should you package the it? And the pack singleton says, oh, I'm ended up here at the end. I didn't find anything. What do you want now? And in this case, well, I don't want anything. I just say assert false. Okay. Now you can do more. I say, okay, return the head. That means it's from actually where the range starts to where I found my thing. That's what I want to have back as kind of a subrange, as a view onto the elements that are before the element that I'm looking for. And that's how you would write it. So the pack is the TC take, which generates that subrange, and the pack singleton, again, is in this case assert false, so I'm expecting to find it. But of course, you could have any other policy. You could say, okay, I want the whole range back, for example. Now, so far we talked about ranges in terms of iterators. And that's kind of limiting. And we found that in most cases where we use ranges, you don't really need iterators. And here's how it works. First of all, there are things where you are enumerating stuff that are not so easily written as ranges with iterators. The typical thing that people quote is traversing a tree. So you would say you have a dialog and you traverse widgets, and for each of these widgets, you want to call the functor. And if you have a window, then you traverse its widgets recursively, and then you have a bunch of first-level widgets, and then you do the traversal there on a second window. And it's a bit like a range in that you got a bunch of things that you can enumerate, but it's not really something you can easily write an iterator for. So you have kind of the encapsulation of a visitor pattern. Now, still, even though you don't have any iterators, you could imagine writing something like this, where you say, okay, the mouse hit any widget. That's an any of you first traverse all your widgets, and then you do something with the widgets that you are being passed. So your range really becomes kind of a functor where you plug in another functor that receives all the elements. What are we really doing when we do this? First of all, let's look at the iterator case, the old case. That's known as external iteration. External iteration means the consumer of the data sits at the bottom of the stack. So I'm basically toiling along, and whenever I need a value, I just reach up and pull the value out. Star it, plus plus, star it, plus plus. So I'm sitting at the bottom of the stack, and you want to pull values out of the top of the stack. You do the call to get the next value. So what kind of consequences does this have? The consumer at the bottom of the stack is always great. You want to be always at the bottom of the stack, because you have a contiguous code path for your whole algorithm. You just walk along, and whenever you need a value, just say I need a value. That makes it easier to write. You get a better performance because your state can be encoded in the instruction pointer. So wherever you are in your algorithm, it basically encodes state that you don't have to encode explicitly. And you have any amount of stack memory. You can put any amount on the stack that you want. Now, the producer at the top of the stack, that would be, in this case, in the old case, the iterator, there it's more difficult. You only have, for each item, a contiguous code path. You always interrupt it. You return your item, and then you get called again. That makes them harder to write, because you kind of have to divide your work into these little pieces. You get worse performance, because you have only a single entry point, which is your operator star, and you must look into your state and say, where am I in my algorithm? And then you have to dispatch to the right place. And you only have a fixed amount of memory, which is kind of the state you can keep in your iterator. And if you want more, you have to go to the heap. So that makes the producer at the top of the stack harder to write. And right now in C++, that's kind of by default always the guy at the top of the stack is always the producer. That's the iterator case. And it turns out that's limiting. You don't really need it. You sometimes it's better the other way around. So let's do it the other way around. That's known as internal iteration. There, the producer is sitting at the bottom of the stack, and whenever he produces a value, he says to the consumer, here's a value. And the consumer says, oh, thank you, and has to do something with that value. Now the producer is at the bottom of the stack and has all the advantages of being at the bottom of the stack, and the consumer is at the top of the stack and has all the disadvantages of being at the top of the stack. Now, can we both be at the bottom of the stack? Yes, in principle, with coroutines. So this is kind of conceptually how they are written. You basically have two programs running, or threads of execution side by side, and the producer says, I need a value, and the consumer runs conceptually on a different thread fiber coroutine, runs a piece of code until he has a value, and with this yield, he would just pass the value over. And then this guy runs a little bit, and changes the flow of execution over to the coroutine again, and so on. So they are basically simultaneously running. Except it's not that easy. These coroutines come kind of in two flavors. One are stackful coroutines, where basically these two control flows are complete flows of execution with a complete stack. So you can do whatever you like. You're not limited by the amount of stack you actually are using. And in particular, you can also yield inside any subroutines that you're calling. So you can call any functions as deeply nested as you want, and deep inside you can still call yield and say, okay, now I produce the value. So that's what you would do in these kind of cases, where the traverse widgets internally would recurse down and somewhere inside say, oh, I found a button here, yield button. Now, they're expensive because quite frequently they are implemented as OS fibers, and then they actually have their own stack, which means you have to allocate 1 megabyte of memory, or at least virtual memory, for example, on a Windows machine. And at some point, maybe you're going to run out of them, and also creating them is quite expensive. This can be optimized to some extent. So far, the standard committee decided that's not good enough. There's a Boost Coroutine 2, I think, is the current library in Boost that implements coroutines. That wasn't picked as for the standard. Currently, there's a Coroutine TS, which is a stackless coroutine. It limits what you can do with a coroutine by being able to yield only in the innermost, or no, in the lowest level function. So in any subroutine that you're calling, like here, traverse widgets, you wouldn't be able to yield so easily any new elements. And they kind of have a funky syntax and a funky way to actually drive them. Take a look at it. It is probably still not as efficient as a pure function call, because essentially what you would need to do for coroutines amounts to a virtual function call. You essentially have to somehow get the flow of execution to the right spot. So inlining these things entirely is going to be very difficult for the compiler. So it turns out, actually, that the internal iteration is very frequently good enough, so that the consumer is happy to sit at the top of the stack. Which algorithms actually work? Which algorithms can you implement with internal iteration? I said find. That's kind of difficult to do because you need to return iterators. Well, if you are happy to return values instead of iterators, I'm just going to copy the value, then actually you can implement even find with internal iteration quite easily. Binary search, okay, that's difficult, you need iterators. But for each, that's okay. For each is actually the prototypical example where you are turning yourself onto the top of the stack. You are saying, oh, I want to receive values out of that range. So for each is trivial to implement. Accumulate is fine. All of, any of, none of is fine. Many of these things are fine. Adapters, the filter, the transform, you can implement all that with internal iteration. So what we did actually in the library is that we have all these algorithms in versions that actually work with internal iteration. Some of them you don't need to do anything special, like in accumulate, for example, would just basically internally use the for each, so you don't need to implement anything twice. The filter and the transform, though, they actually work a little bit differently. They basically take the value, the filter would look at the value and say, is that good for me? If that's not good for me, I'm just going to drop it. If it's good for me, I'm just going to pass it on to the higher level function, or to my consumer. That's, in this case, sitting at the top of the stack. So this is an any-of implementation using internal iteration. Quite simple. So you take an any-of for range, and I left out the predicate, any-of of range, and you're saying, okay, the result is currently false, and then you enumerate all the values in your range, you take them, the bool context actually makes sure that you get a contextual evaluation to bool, which you probably want in this case, and then you have b result equals b result or b. So the b result, anytime there is any b that is true, the b result would also be true, and then you end your iteration here and return the result. Is that good? Not quite, because any-of is lazy, and we want to preserve this laziness. It makes sense to preserve the laziness. So the thing is, we need to somehow, while you are running this enumerate, and we are somehow here, and discover, oh, b is true, fantastic, we can abort, you need to somehow say, abort, stop. Hey, enumerate, stop. So how do we do that? You throw an exception. No, that's too slow. That won't work, okay? So I need to come up with something better. And there are not too many options here. We said, okay, let's say we have an enum. And the enum says it's either break or continue. The nice thing about the break or continue is the enumerate can actually check what this thing is returning at compile time. And if you are returning break or continue, you know that the guy wants to break sometimes. And I need to put in the checks to check, is this guy returning break? Now, if it doesn't return ever anything like break or continue, if it returns void, say, then I know this is never going to break, right? So I can just leave out the check entirely at compile time. And that's kind of nice. That makes things efficient. Now, here's what I just said. So break or continue, we check for break. Otherwise, we don't need to do anything. You would think that, well, maybe these are very special cases because we are now just optimizing stuff for iterating through dialog widgets, which I don't do very often, so why do I care about all this stuff? So it turns out that some of these adapters you can actually implement more efficiently when you have internal iteration. Don't look at this yet. There is one that I actually showed you, which you can actually implement more efficiently, which is the filter. The filter usually works something like this. You generate a value, you look at the value. If that's the value you like, you stop. If that's not the value you like, you drop it and you increment your underlying iterator. That's the implementation we saw for external iteration. Now, how's that going to be called? Well, someone like consuming stuff is going to do it like this. It's going to be called plus plus. So at the time of plus plus, I'm generating the values from my underlying base and look for one that passes my filter. Ah, I found one. Great. So here's one that that passes my filter. What am I going to do with it now? Nothing, because I'm just got a plus plus. I just got an increment. So I drop it. Now someone comes along and say, now dereference that iterator. Well, now I have to go to the underlying range and say, please, could you produce this value for me again? And it produces a value again, and you look, and you just take it and pass it out. As long as that underlying range is nothing more than a vector, that's all great. But if it's anything more complicated, where you actually have to generate the value in a costly way, that's not ideal. If you write this with a generator, on the other hand, you can do it more efficiently, because you get the value passed to you, you can check it, you drop it if you don't like it, but if you like it, you immediately pass it on to your consumer. So there, you're actually saving generating the value twice, which is nice. Now there's a concat, and it actually has a similar advantage. So usually, when you are doing an increment on a concat, every increment is a switch, because you need to know, am I still in the first range, and then I have to increment the first range, or am I already in the second range that I'm concatenated to that first range, and then I need to increment it. So the iterator, the operator plus plus, essentially, has to do a switch every time, and I'm still in the first one and the second one. And next time around when I'm called, I forgot already about that, whether I was in the first one and the second one, so I have to check again. I'm in the first one and the second one. So you have this check every time you're being iterated. That's stupid. Oh, the dereference has to do it as well. They also need to know, am I the first one or the second one? Either I'm index 1 or I'm index 2. I mean, these indices are essentially variants. I'm either having an index 1 or an index 2, one of the two, and every time I have to check. Now, with generators, I can simply write this. I first iterate through the first range, and when I'm done with it, I iterate through the second range. And that's very efficient. I'm just as efficient as you would do this yourself, where you would iterate through these things individually by yourself. So there, you can actually write things which are usually iterator-based more efficiently if you use generators. So, that said, here's the URL of the library. You can download it and take a look. And I hate the range-based for loop. Why? Because people start writing this. If all I have is a hammer, everything looks like a nail. There's 4. So I write 4s, and then again, I pretend I do range stuff, and I write oh, I'm using ranges because it's a range-based for loop, but internally I have an if again, and blah, 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 and be true, and blah, blah. Instead of writing this, any off range is prime. Thank you very much. And questions, I suppose. No, but what we ensured is that all these things that we implemented, if you just do inlining, if you inline aggressively enough, you would get 0 overhead. So, do I know how well the compilers are actually inlining? No, we didn't. We looked in easy cases, and yes, it did it. But how much does it do it in complicated cases? I don't know. Is it going to improve over time? Hopefully. But what I'm just ensuring is that this is optimizable. And that's the important thing. I'm not creating a contraption which locks us into non-zero cost abstraction. This is still zero cost abstraction. If you just inline it aggressively enough, even when you build these huge adapter stacks, if you go through the operations that they're actually doing, you would have to do exactly the same operations by hand if you would actually run this algorithm by hand. So if you collapse it, it boils down to exactly what you want to do. And that's all I can do with the design of a library, really. Anything else is then up to the quality of the compiler and the implementation. So I never actually thought about it. When I started ThinkCell, I was basically dead afraid that in 10 years, I would have 1 million lines of code that I wouldn't understand anymore, that become unmaintainable. And so there was just no question that I have to do everything in my power now to avoid that outcome later. So there was basically no actual alternative to doing this. I mean, if you refactor, if you build new stuff, then the cost is immediately clear because you build the new stuff here and now, and then you use it. So you know that at every given time, your code base is in a good state. You exploited how you programmed it as well as you could. Now, if you don't do it, maybe it's good enough, but maybe it turns out 10 years later that it wasn't. And then you are in a deep, deep hole, and you take a whole long time to dig yourself out of it. So I am convinced. I mean, we have now 20-something developers, and they are dealing with a pretty big code base, and they're writing a whole lot of software that we sell to a whole lot many people. So we're doing something right, and that could be because we just have developers who are so good. And I think that's part of the story, a large part of the story. But I would like to think that it also makes a difference that we try to build libraries, and maybe even building the libraries helps keeping the developers because they're actually interested in working on these kind of libraries in between. And that's, yeah, maybe that if it's just for keeping people happy. But I would like to think that it's a bit more.